Good afternoon, everyone. So, T has corrected the homeworks and I posted the grades on Canvas. Those of you who got about 70, 75 after the grades have been normalized, that's a decent place to be in. But if you've gotten below that, I would put more attention on the homework. Make sure you don't even miss a single point in the homework so that you can bring your grade back to an A minus or even possible A. But if anybody wants me to change anything in the way I teach or the homeworks that I give, if you want more time or anything that will help you improve the grade, do not hesitate to let me know. Just shoot me an email or you can come to my office anytime and we can sit and chat. So the second thing is there is a project component. We'll start the project starting next week. So we'll meet in the lab in the Keller Hall 3146. I have posted a section on module on Canvas. If you go to the Canvas page, there should be a new section right on the top, the project. So in this, go to the first link. So there should be the project. If you go to the first one, meeting time, there should be a link there that you can go and select what time slots are available. Select as many as possible that you're available to meet for the next 3 weeks. Because there are quite a bit of number of students and I want to keep it within 3 sessions. So the more number of slots, it's easier to organize. So make sure you fill this in by this Friday. When you submit your homework, make sure you submit this as well. Because I need to go and decide the time slots. And then on Monday, I'll post the time slots that we'll meet at. All right, so we'll meet in the lab and we'll do these bunch of experiments to get the values that then we can use to submit the project. So make sure you do that. Everybody is required to do attend the labs to complete the project. Otherwise, you can't complete the project. And that's one easy way of scoring 25% full block of score, right? Last time everyone got full score in the project. So do make sure that you come to the lab and do the work to get the full score for it. Okay. And I also posted another module for internship opportunities and RAs that as they come up, I'll just let you know. If anybody is interested, just take a look at all three. The first one is particularly very enticing because it's just like a couple of hours of work a week and you get 25% coverage. They'll cover your salary, they'll cover your tuition and everything. And it's basically just helping other people do the lab. So it's a very easy task and they prefer someone who would stay here for at least 2 years. So those of you planning on doing a master's would be a very good fit for it. But if no one applies and there are no master students available, then they would even consider undergraduate students. So do consider applying for it. The other 2 positions, let me know if you're interested. I can send them an email and CC you so that you can get a good referral for it. Okay. With that, let's get started with today's class. So today's class, we're going to be looking at just a quick review of control systems and how we can go ahead and control our motor. And whatever we learn today, we'll be carrying it over for AC motors as well. The concept is very simple. So before we jump into that, let's quickly just do a review of what we looked at last class. So we modeled our motor as these 4 equations. So we have our electrical system equation, we have our mechanical system equation, and then we have our electromechanical system coupling, which basically is the relationship between speed and the EMF, and then the current and the torque. Right. So we have these 4 set of equations, and we can represent this in transfer function form as well. Just take the Laplace of this. So V of S minus E of S equal to SL plus R times I of S. So that's just the I of S divided by V of S minus E of S 1 by SL plus R. And similarly, you can get the mechanical system transfer function as well. And we can model this whole system in just this transfer function form. So in the homework, I had asked a couple of questions. So one of them is what is the time constant of the electrical system, and the other one is what is the time constant of the mechanical system. Whenever you model any kind of system, whenever you do MATLAB simulation or any numerical simulation, one of the difficult tasks, other than building the model itself, is choosing the right solver and choosing the right step time so that your system can converge. In a very simple system like this, it's straightforward and obvious what the step time should be. But when the system gets extremely complicated, especially in nonlinear systems, depending on what step time that you choose, you can get results which would look stable and correct, but might not be the actually correct results. In a linear system, that won't happen. Just by looking at the results, you can tell that the step time is not good enough and you can reduce it. But higher order systems and nonlinear systems, that's a very difficult proposition. So in our system, to decide what the step time for simulation should be, we need to understand what the time constant of the system is. So what is the time constant of the electrical system? From the equation that I have on the right there, what would be the time constant of the electrical system? Anybody?
L over R.
L over R. Thank you, Hannah. So L divided by R. Right. So if you look at this transfer function, you can represent this as take the R term out of the picture. So take the L term out. Right, and then you have R by L. This is equal to 1 by tau, a time constant. Right? So our time constant of the system is going to be L by R, and the time constant of the mechanical system is the same thing, J by B. And if you remember when we had our RL network, the time constant was basically the amount of time it took to reach that 63 point some percent. Right? So that is one time constant. And that was equal to L over R. So for a typical system, for example, in the lab motor, this is in the order of say 5 milliseconds. And this is roughly in the order of around 1 to 2 seconds. Okay. So given these values, how do you choose your step time for your simulation? Can I choose a step time greater than 5 milliseconds? What would happen if I choose a step time greater than 5 milliseconds?
It wouldn't converge
Why wouldn't it converge?
because you're sampling too fast, or you're not getting to see the full potential.
Okay. So it depends. So I wouldn't say it wouldn't converge. There is still a possibility that it could converge. It would not converge to the correct value. Right? So if you say it doesn't converge, that means the alternative would be diverges. You can still choose a wrong sample as step time and the system can converge. It will just not converge to the correct result. And the problem is because if you give a step response and you compute the value here and you compute the value, let's say at 2 time constants away, you're not capturing every single point as close as possible so that you can faithfully reproduce the original trace signal. But let's say the thumb rule would be look at the smallest time constant that you have in your system and use at least a sample time, step time in MATLAB, T step, of at least the 10 less than 1 by 10 of your smallest time constant, right? TC. So in our case, the smallest time constant comes out to be 5 milliseconds. Choose a value of at least 0.5 millisecond, or worst case 1 millisecond, or if your computer is fast enough, you preferably want to do smaller and smaller time constant, smaller and smaller step times, right? So there's another interesting thing here, which is that if you look at these two time constants, what this essentially conveys is whenever you see this time constant term, what it essentially conveys is if I give a step change in the voltage in this electrical system, let's assume the EMF is 0, it's going to be 0. Let's later figure out how we'll make that happen, but let's assume this term is always 0. We apply a step voltage. This basically shows how quickly your signal will respond to the step change and settle down to your steady state value, get closer to the steady state value. The same thing, if I apply a step change in the electromagnetic torque, it says that the mechanical system will take far, far longer to settle down compared to the electrical system. Right? That's all this time constant term is conveying. It is that for a step change in the voltage, your electrical system would converge way faster compared to a step change in the electromagnetic torque, leading the mechanical system to converge. When I say mechanical system converge, what I mean is the speed. So in this case, in the electrical system, this was the plot of the current. In the mechanical system, it's going to be the plot of the speed. It's going to take far, far longer. Right? It's not even on the same time scale. It's like 1,000 times bigger. So I'm not doing justice by drawing it here. It should probably be the whole board length. Right? So for the same step change in electromagnetic torque, your speed is going to go much, much slower. And this information will become useful to us when we design a control system in a little bit on Friday. But for now, let's just put a positive. Okay. So today's class, what we want to be on Friday's class, what we want to essentially do is design some kind of control system so that our speed does not change irrespective of what load torque our motor is operating under. So let's say I put some 10 volts in the motor and the motor has gone to 100 radians per second and there was initially no load torque. As soon as I apply a load torque, what's going to happen to the speed? Is it going to reduce or it's going to go up?
So reduce.
Reduce. Why is it going to reduce?
Compensate for Mechanical energy being taken away by the load.
Perfect. So as soon as you increase the load torque, the mechanical power, output power going out of the mechanical system, that's going to be the load torque times the mechanical speed. So the load torque increased, let's say the speed remains the same, the output power suddenly increased. And the output power, can it come from the input side? Where does that increased output power demand get satisfied from? Is it coming from the input? Let's say it's not coming from the input, where else can that additional demand for energy come from? Do we have any energy storage elements in the system?
Motor inertia.
Motor inertia. So there's some amount of energy stored here. Whenever we have some rotational aspect to it, there's going to be some inertial energy, half j omega square, stored in our rotor inertia. And as soon as this additional demand for power comes through, the electrical system can't suddenly satisfy it, because for the electrical system to satisfy it, then the current must increase. But the only way the current can increase if the voltage is a constant, if the EMF changes. And the EMF can only change if the speed changes, right? So before this energy can be taken out from the inertial system and then the speed can reduce, there is no additional power coming from the input side. So the only source of energy that it can tap into is the inertial energy stored here. So what then happens is take some energy out of it, starts to bleed the inertia out, right? Inertial energy out, J does not change. So the omega has to come down, because taking energy out and giving it to the output power satisfy the additional load demand, which means the omega has to come down, right? Because energy goes down, omega has to come down as well. And once the omega goes down, then we can come back to this equation. Our EMF comes down. Once the EMF comes down, V minus E becomes larger, right? E is reducing. So V minus E will be increasing. This is a constant. So once V minus E increases, this term, the current is going to increase, right? So if you look at the current, it's V minus E divided by SL plus R. In steady state, let's assume this LDA by dt term goes to 0. So it's just the difference divided by R. So if this term increases, the current is going to increase. If the current increases, the torque increases. It will increase up to a point where the new load torque is completely satisfied by the added load torque is satisfied by the increase in the electromagnetic torque. Once that happens, it no longer needs to draw energy from the inertia. But it will now go and settle down to the new reduced speed though, right? And as you keep on increasing your load torque, the same thing keeps happening. It initially takes out from the inertia, and then the speed will reduce, and then the EMF will reduce, and then the current will increase, and then the electromagnetic torque will increase to a point where it will satisfy the newly created added load torque. Yeah, Thomas.
Why does it take energy out of the inertia before taking energy? This might be a dumb question, but out of the magnetic field of the inductor.
So it would take out energy from the magnetic field of the inductor too, but the energy stored in the magnetic field of the inductor is very minimal.
Okay.
Half j omega square will be much, much larger than what you'll get with half Lx square.
Okay.
Any other questions? Okay. Can you give me another reason why can you tell me how much the inertia energy in the magnetic field will reduce? When the load torque increases, would the energy in the magnetic field reduce or would it go up? We clearly saw the energy in the inertia goes down, right? Once it settles down, it will definitely settle down at a lower speed because half j omega square. What is the formula for the energy in the magnetic field?
It'll go up because the current increases.
Okay, so we have half Lx square there. Okay. I will have to go up because of this increased load torque, which led to increased electromagnetic torque, which means I went up, which means the final energy in the magnetic field would end up being higher than what it was before. Right? Yeah. Sure.
Does the energy in the magnetic field actually matter for any reason? Do we really care about it, or is it just kind of there?
There is so in case of this DC motor, that is just there. It is not particularly useful. It does become a problem when we have that commutation sparking, because let's say we have 6 coils. 1/6 of the coil is commutating, so 1/6 of the magnetic energy would have to go out and reverse in direction, right? So for the arcing point of view, it will be a problem, but otherwise for these operations, it's not an issue. Any other questions? Okay. So today's class, let's try and figure out how to find out all of these 4 parameters for our motor. So in our motor, we typically have control of what the output voltage, the terminal voltage is. When I mean terminal voltage, There's nothing special about it, just the terminal wires that are coming out, what voltage we can apply across it. So that's the only one element that we can control. The other element is the load torque. It may or may not be under our control if it's connected to like an elevator or something that's typically not under our control, number of people getting in and stuff like that. But you can put a constraint of the maximum load torque that can be possible. Or in some cases, those of you who have done the lab already, you would typically clamp the rotor when doing some parameter estimation. In those cases, you can make sure that the load torque is such that it matches whatever the electromagnetic torque is. Right? So there are some variability of control. Sometimes you can, sometimes you can't. So let's say these two variables are something that external that we can control for the most part. Then the other two variables in our equation cannot be controlled. So the I and the E, these two then no longer become are under our control, as we saw last class or the class before that, right? So these two are uncontrolled. In the situation that I've shown. Right, so whenever we want to figure out these parameters, these 5 parameters, all we can control are the voltage or the load side, the torque side. And then we can only measure what the current and the EMF are. And again, going back to the EMF, we can't directly measure it. What can we measure to figure out what the EMF is in a motor? EMF itself is not directly measurable, right? So what else can we measure in a motor that so that we can figure out what the EMF is?
EMF equal to KT times the speed.
Perfect. So to know the EMF, all you need to do is measure the speed, and measuring the speed is pretty easy. So if you can measure the mechanical speed, your EMF is just Ke times the mechanical speed. And again, this Ke term and KT term, as we derived last couple of lectures before, they are one and the same. If they are both under the same units, right? If one of them is volts per RPM and the other one is Newton meter per amps. So if you have volts per RPM and then the other one is Newton meter per amp, they definitely won't be equal, because the SI unit for that would be volt second per radian, right? Because this would be radians per second and this would be voltage. So volt second per radians, and then if this is Newton meter per ampere, then these would match. Right? But typically in the data sheets, when you see Ke and KT would be different values, because people like to give this in terms of pounds or something, and this one in terms of Newton meter per ampere. So they're completely different unit bases. So the values might differ, but if you convert them to SI units, they would exactly match up, right? So in our course, whenever I use Ke and KT interchangeably, they mean one and the same. It's just some K. So once we measure the speed, we can directly figure out what the EMF is going to be. Current, that is something that we can directly measure using some kind of current sensor. So this is a measurable entity as well. Okay. What is the one scenario in which I can actually figure out what the EMF is? One operating point. Yeah.
I had a question. So KE and KL are like attributes of the motor, so will those be given to us, or is that ever something we have to calculate?
It's depends. So in the project, I've asked you to calculate the KE value. I give you the motor winding distribution, and then I ask you to figure out what the KE value is going to be, right? If you look at a data sheet, typically they'll give you that value in a data sheet. Sometimes you'll have motors that you don't have the data sheet for, or the KE value is not known correctly, right? In those cases, we'll estimate the value by doing some experiments. So depending on the situation, we can either get it from the data sheet, or we need to estimate it, or if you have the winding diagram, you can compute it, right? All right, so what is the one situation under which I can actually measure the EMF? Yep.
Is it steady state of the omega?
Steady state of omega, correct? So I still can't directly measure EMF, right? Even in the steady state of omega, I take the omega value and figure out what E is. And this is the relationship is not a steady state relationship. If I know omega, even if the omega is changing, then the EMF will change exactly like this, right? Just scaled by some scale. So none of these equations are steady state equation. Yeah.
There's no current. Could you measure E because it's just equal to V?
Perfect. So when there is no current flowing in the system, this term is 0, this term is 0, V is directly equal to E. Right? So if I have a motor, can you give me a setup where there will be no current in a motor? But there will be any voltage across the motor? Is it operating as a motor in that case? What is it operating at?
A generator?
Yep, it's a generator, right? If you take energy out of it, it becomes a generator, but basically you have some other system connected here. Some other motor or water, so some water flowing past some blades, creating some energy. So the system is freely rotating, and then this is going to create an EMF, right? Because it's rotating, going to create an EMF. That EMF is going to be appearing as a voltage if there is no current, if there is nothing connected to the outside world. So this is one way we can directly estimate the KE value. So we already have our answer there for how we can figure out KE. Take your motor, connect it to another motor, and spin this other motor while keeping this terminal open. And figure out what the speed at which it's rotating, measure the voltage. Your voltage divided by your omega, that is going to be your KE value. Again, for open circuit condition. Open circuit motor. So in that case, V is equal to E. So that's why we're able to make this relationship. Right? So, all right. So now let's go ahead and estimate the rest of the parameters. Can somebody tell me how you'll estimate the resistance? How do you estimate the, you don't have to think too hard. It's a very simple answer. Yeah, Thomas.
The voltage on it and measure the current.
Perfect. So put a voltage on it, measure the current. That's exactly what a multimeter is going to do for you. Just take a multimeter and measure what the value is going to be, and it's going to give you the resistance. There are a couple of problems with doing this method. I'll get to that in a second. But once we have the resistance, can somebody tell me how we will measure the inductance? How can you get the inductance of this circuit? Again, the answer is already on the board. Yeah,
From the time constant,
fantastic. From the time. What was your name again? Sorry,
Olivia.
Olivia. So we already have the diagram there. So we apply a step in the voltage. What will the current, let's say I apply a step voltage of 10 volts. So I have the voltage at 0, and then it goes to, at time t equal to 0, it goes to 10 volts. And let's say the resistance is 1 ohms. What is going to be the steady state current? 10 ampere. So the steady state current is going to be 10 amperes. And if I wait, if I figure out where it goes to, let's say 6.3 amperes, right, whatever the value comes to 1 minus 1 by E times 100%, right, of 10. So wherever that value comes out to, if I stop and look at the time, that is going to be equal to L by R, question mark. It may not be, as we'll see. But if that were the case, then if that is some time E, I know already R, so I can figure out L from this value. There's a very big problem with this. Can somebody tell me what the issue is going to be? It's a very good answer. But there's a mistake in that model. Going back to our equation, the diagram that I've drawn, there is an equation for V equal to L di by dt plus Ri. It has completely ignored the EMF term E. Right? The problem is, as the current starts to increase, there is going to be acceleration because the torque is increasing, then the speed is going to increase, then the EMF term is going to creep in. So when I take a DC motor and apply a step voltage, that is not the waveform it's going to look like. Right? Because it's not just V across an L and an R, it's a V minus E across L and an R. Even though V is a constant, E is a varying term. So the picture is far more complicated than what I've drawn there. But what can I do to ensure that that's the shape in which the current would look like? There's something I can do in the motor to ensure that that's how the waveform would look like. What can I do?
Spinning.
What was it?
Keep it from spinning.
Keep it from spinning. Perfect. So if I somehow hold on to the rotor, right, I could use a mechanical clamp of some sort. If it's a small enough motor, I can hold it by hand and ensure that the rotor is not rotating. Then the EMF term can be ensured to be 0, and then that is the waveform that I'll definitely get for the current. And then I can go ahead and do all of this analysis. So there is quite a big of a problem here. We are putting a constraint that the voltage, the speed has to be 0, which is not always possible. If you have a very high power motor, you cannot typically put a clamp on the motor. It will rip the clamp apart if you try to hold it by hand. I don't want to see there what's going to happen. So it's not always a feasible solution. So what else can we do? How else can we estimate the inductance in the case where we cannot clamp the motor so that the speed remains 0? What else can we do? When I introduced this diagram in the third or fourth lecture, I gave another interpretation for time constant. Does anybody remember what was the other interpretation for time constant? So if the current were to rise at the same speed, at time t equal to 0, let's say it started to rise. And if it continued to rise at the same linear speed at which it started off rising, because of the inductance component, it starts to kind of, because of the resistance component, it starts to kind of narrow down. But if it was just a purely inductive network, this would have kept on increasing forever, right? And the time it would have taken to reach the steady state value in this inductive resistive network is the value of the time constant, right? So at time 0, look at what the slope of the current is. And from that slope, I can figure out what the time constant is going to be, because if I look at the slope line, how long it will take to reach the value of 10 ampere, then that will be the same as the time constant that I had before, right? What is the advantage of this? Do I need to keep the voltage on for always? So even in the previous setup, do I need to keep this voltage at 10 volts forever? At what point can I shut off the experiment? Do I need to wait till it gets to 9 amperes or something closer to the steady state current? Or can I shut off the experiment much earlier?
Anytime after you get that impulse.
Perfect. Anytime after I get to this 6.3 amps value, right? I just need to know how long it took to get to the 6.3 ampere value. After that, I can just shut off the experiment, let the current decay. The rest of the performance is totally irrelevant to me. Now coming to this one where I just need to get the slope of this, when can I shut off the experiment? This is the slope of current at what time instant? Whatever straight line I have drawn there, that is the slope of the current waveform at what time instant? 0. So it's the slope at this time instant, because if I drew the slope at this time instant, it would have a different value. And this would be the slope here. If I go farther and farther out, the slope would be much, much different. So if I draw almost when it settles down, the slope is very close to 0. So whatever the slope I've drawn here is just a slope at the time instant, current at time instant equal to 0. So it is I prime at t equal to 0. How do I get this in a discrete domain? Let's say I'm sampling this current at every time instant. Let's say I'm sampling it every 0.1 millisecond, right? How do I get the slope at time t equal to 0? What is di by dt? I did when Ben asked the question couple of 2 classes before, where he said that the differential operation is preferred over integral operation because it's numerically less expensive. I did show what the operation of di by dt is, right? It ended up being exactly the same as the integral operation. So how do you find out the differential in discrete domain? Yes,
You just have like a really tiny time step and then just calculate the slope off that.
perfect. So if I take a tiny time instant and look at what the current is, some delta t, it would be some current I at time 0 plus delta t. Right? So I figure out what the current is at time 0 plus delta t, which is at some time delta t. What would have been the current at time t equal to 0? 0, because we just started the experiment with no voltage before that, divided by delta t. That's it. So it's just I of delta t divided by delta t. That is going to be the slope of this line. So all I need to do is run this experiment, put a tiny amount of, put a 10 volts voltage, just for 1 millisecond, or however small my ADC or whatever measurement device I have can sample the current, right? And right after that, I can shut off the experiment because I just need the slope of that curve alone. Nothing else is needed for me. So right after the time step, I can shut off this experiment. Again, here I'm drawing this over exaggerated 1 millisecond with just a very tiny value. The current wouldn't have built that much, but di by dt would have been quite a large value, right? So this term is all I need. The one sample time look at what the current is divided by the delta T, and I can shut off the experiment and let the current decay. There's nothing to decay, it's very close to zero, but the dA by dt term would not be zero, right? So what is the advantage of this? Do I need to clamp or hold on to my rotor to prevent it from rotating? There is no requirement, right? Because the current just lasted for one instant, there wasn't enough time, because if we go back, this is where the time constant becomes very important. Our electrical system responded, but our mechanical system is going to take a long time to respond because it's orders of magnitude higher in time constant. So mechanical system won't have enough time to respond. So our rotor never rotated, our back EMF term never came into the picture. So we are faithful in our reproduction that it will be equal to LdI by dt plus Ra. What would the slope be equal to? Well, we can work it out numerically. We can work out the equation and figure out the value, but there's a much easier way of figuring out what the slope would be. Does anybody have a feel for what that slope would be? Go back to our electrical system equation, right? So we have E equal to E plus L di by dt plus Ra. In our current setup, what is the value of E? 0. So this term goes away. What is the value of Ra going to be? Approximately, what is it going to be? 0. Because the current is again very small. It is the current is very small and the delta T is very small. So the division of small current and small delta T becomes appreciably large. But the current magnitude itself is quite small. So this term is negligibly 0. So what is the slope? That is di by dt. If delta T gets to 0, as it tends to 0, the limit becomes the differential. Right? So our slope is equal to V divided by L. We know what voltage we applied. We applied 10 volts. We know what di by dt is from our measurement. Then we can get the inductance L. L equal to V divided by di by dt. Right? So we could have looked at the same thing the other way around as well. So from our definition, we said our time constant is equal to the time it takes for the slope to reach the steady state value. So let's say it takes some time t. Okay? If I multiply this time t by this value, right, whatever slope I got, which is I of delta t divided by delta t, that must be equal to whatever the steady state current would have been. And what was the steady state current? That was equal to V divided by R. And what is my time constant? It's L divided by R. R cancels, we get the same formula again, however you look at it. Di by dt. Again, this term tends towards di by dt as delta t tends towards 0. Right? So it has quite the advantage that without locking the rotor, you can get a quick estimate of the value. Alright, so but this all depends on knowing the resistance. If we didn't know the resistance, then we run into a little bit of a problem. Right? So what can we do to figure out the resistance on it? There is another problem. Are these resistance and inductance in the motor always a constant? Can you tell me an instance when the inductance will change? We have already visited that. Well, let me start with the easier one. Can you tell me an instance when the resistance in the motor would change?
Increases with heat.
Increases with heat. So as the motor keeps rotating, we have I square R loss, we have B omega square losses, we have hysteresis losses, eddy current losses, sparking. The first two we have modeled in our system, the hysteresis, eddy current and sparking we haven't modeled. Right? But all of these losses contribute to heat and it will start increasing the motor temperature and reach to a much some higher temperature. And as the temperature increases, your copper resistance starts to go up. Right? In a simple model, you can assume the lattice is oscillating more, so the mean path length of the electron is reduced, so the resistance starts to increase. Again, not the full picture, but you can just make a simple assumption. So resistance goes up in that scenario. Can you tell me what would happen to the inductance typically? As we start pushing more and more current into the motor, what is going to happen to the inductance of the motor? Thomas?
Doesn't it change to like a capacitor or something like that? Or like the windings?
Interwinding capacitance is the way that is a function that comes when you increase the frequency of the system.
Oh.
Right, as you keep, that was the fourth question in your exam. Right, as you keep increasing your frequency, what previously behaved as an inductor could start to behave like a capacitor. Right, but we are not changing the frequency here. We are just increasing the magnitude of the current. Yep, Jono.
Would it decrease because of saturation?
Perfect. So the inductance will start to decrease because the core starts to saturate. If you remember when we looked at the reluctance of a C core with an air gap, we ignored the reluctance of the ion because we assumed the permeability was infinite, only the air gap mattered. But as we start putting more current, the core starts to saturate. We can no longer ignore the permeability of the core. Core permeability also comes into the picture. So our reluctance starts to go up. Right? So our reluctance was L divided by mu R mu naught A. So if this mu R is very large, then for ion we could ignore it. We can only consider for air gap. But once the starts to saturate, mu R gets closer to mu naught. So it starts to behave like air gap. So that offers more reluctance as well. And our inductance itself was N squared divided by the net reluctance. Right? So as our net reluctance starts to increase, our inductance starts to go down. So typically when you have these motors at 0 ampere, let's say you have 5 millihenry, at rated current that would be as low as 30% of the 30% of 5 millihenry. So core does quite saturate, goes deep into saturation as you start to exceed the total rated current. Right? So all of these parameters can change. So whatever we estimated at steady state at the simple case where the motor wasn't running and you just put these measurements and measure would not be the same as the motor starts to rotate. So we need to be able to have some kind of method where we can estimate this on the fly. Can anybody think of another method? So we looked at the step response for an RL curve with which you could measure the L value. Did we look at any other methodologies of analyzing this RL network? So let's say we start to apply an AC voltage into this RL network. What is going to be the relationship between the current and the voltage that we apply? Let's say this voltage is some V sine omega t and L and R. What is going to be the current? Pretty straightforward. So we just have our current magnitude is going to be V magnitude divided by square root of R square plus omega L square. And the angle of the current is going to be tan inverse of omega L by R. This expression is also something that we have seen before when we did our Fourier analysis. Right? So now what we can do is we apply some sinusoidal voltage. In our current measurement, we need to make two readings. One is the time at which the current goes to 0 compared to when the voltage was 0. And what would that give us? That would give the phase angle. Right? Because if this is V sine omega t, then the current is just V divided by this, whatever this impedance is. So let me call this I magnitude. Right? So magnitude Im sine of omega t minus phi. Right? So it's just going to be phase lagging whatever the current is going to be, and assuming time in this direction. And the magnitude itself is this value that I have here. So all I have to do is look at the sign, the current measurement, see where it crossed the 0 compared to the voltage crossing, and then see what the magnitude of this is. I have two values and two unknowns, omega and L and R. I can solve two variables, pretty straightforward, right? So I don't need to know resistance. If I inject sinusoidal current voltage and measure the sinusoidal current, I can figure out what the R and L values are. There is absolutely no problem putting a sinusoidal voltage into a DC motor, as we'll see when we do the lab experiment. Right? But what is the problem with this? When Olivia gave the answer that we wait for one time constant and look at what the current is, what was the problem with that? Why did we do this tiny di by dt term instead of using the time constant method?
EMF is not 0.
EMF is not 0 because the motor would start spinning. We would have the same problem here. Right? If we apply some sinusoidal voltage, you'll see the speed will go sinusoidally as well. Right? But what can I do to address that? I don't want to make the voltage too small because the current would be too small. Then I can't differentiate between the peak and the 0 crossing. The measurement will all get pretty bad because of the noise that we have. So what else can I do? I want to keep the sinusoidal thing because I can get both information, but I don't want the rotor to rotate. So try to get an intuitive feel for what's going on here. When we did our first power electronics course, the review, I showed you the lamp blinking experiment. Right? You saw the blinking only up to a certain frequency. Once I went to very high frequency, you completely stop seeing the blinking. I can do the same thing here. If I make this voltage frequency go extremely large, then the motor cannot see the variation in the voltage. Right? For it, it's just going to look like an average value. What is the average of that sine wave? 0. Right? So if I take this voltage but make the frequency extremely large, then during the first half, the motor will try to spin in the positive direction. Next half, it will rotate in the negative. But it happens so fast that it will just wiggle around in the same place. And we'll see that in the lab, it will just go, but it won't move at all, rotate effectively to create a high enough speed that the EMF starts to interfere. So we can still treat this as an RL network. And there is a very big advantage with this method because what we can do is, even when the motor is operating, let's say we have some DC voltage going into the motor is actually spinning and operating and doing everything. We can inject this very high frequency voltage signal on top of this for some amount of time. Okay? And this is not going to do anything to the speed because this is a very high frequency that the motor speed mechanical system doesn't even see it. But if you look at the current would be different because the current time constant is much, much smaller than the mechanical time constant. Right? So even though the speed does not see it, if you look at the speed, so this is the voltage that we apply. This is the plot of the current. This is the plot of the speed. So if you look at the speed would have been very flat. It would probably wiggle a little bit, but that's about it. But if you look at the current would see that sine waveform. It should be the same frequency, right? It's a linear network. Frequency is preserved. Right? The only thing is it will be phase shifted. The time this goes to 0 versus the time the voltage goes to 0, there's going to be a time difference. That is going to be phi. We can figure out what the magnitude is, subtract the DC magnitude out, that gives you the AC magnitude, and then you can do the rest of the expression and calculate the values. So this is called online parameter estimation. In the lab, we don't do this, but for most of the motors deployed in the industry, at least for high performance, they do this. In electric vehicles and stuff, they would inject high frequency components so that the inductance and the resistance are updated continuously so that you can tune your controller. When we look at how to tune the controller, we'll see that these performance is closely linked to what the R and L value are. If you assume some R and L and the value changes over time and you still have the same old controller, your performance will start to deteriorate. So you want to keep on online updating it. So we have this advantage when we inject this high frequency component. Anybody got any questions? Right. So let's go back to, we have already seen how to figure out R. We have seen L, we have seen K. Let's look at J and B. Can you tell me how we can figure out B? Let's again not worry about the online estimation method. For mechanical, it gets a little bit more trickier for online estimation. Yep, exactly. Yeah, but for that I need to know J and time constant, right? I don't know either of it. Let's say I just want, I don't know this term, I don't know this term. Let's say I want to start off with measuring out just what B alone is. Once I know B, then I can use the time constant method to figure out what J is. How do we figure out B? Well, we can apply different voltages to the motor. It's going to cause different currents. Take a reading of the currents. Then we know what the electromagnetic torque is. Let's assume we are not applying any load torque. We are not loading this motor at all. We are letting it spin freely. Right? The motor is not coupled to anything else. It's just going to rotate freely. What is going to be at steady state? This term is going to go to 0. So our electromagnetic torque is directly equal to B omega. Our electromagnetic torque itself was directly equal to the current times the KT. So I apply some V, let it reach steady state, and then measure current. Right, once I have current, KT times I, our electromagnetic torque is equal to KT times I, and this must be equal to at steady state. Now, well, term which is 0, we are not putting any load torque. This is our intentional design. J d omega by dt. This term is 0 at steady state. Okay, that is the definition of DC steady state. All the differential term goes to 0. Only term that remains is B omega. So our B is just, we can again measure omega. It's just KT times I divided by omega. So with that, we have our frictional coefficient B in our motor. How do we estimate J? So, Zach already gave the answer. That if we know the time constant, then, we know B now, we can get J. Now the question is, how do we get the mechanical time constant? What can we do?
Go to 10 amp steady state and go to 0 amp with the step.
Perfect. So we can start off at a known current. So we can do the reverse of that 1 by SL plus R thing. Right? So let's say we are running at some constant speed. We are already putting some torque. Let's say this is our current waveform, which is same as a torque waveform, right? Because torque divided by kT is just a scaling constant. So if I just draw this without any axis mentioned, current and the torque curve are going to be the same. And here I'm going to torque the plot of the speed. Right? So the motor has reached steady state, it's having some current, it is having some speed at which it's spinning. Now what I'm going to do is I'm going to suddenly shut off this current. So that means I've suddenly shut off the torque. What is going to be the speed response? Perfect. So whatever Thomas sketched in his hand. So exponentially starts to decay. Okay. How do I get the J from this diagram?
Find the slope when you initially turn it on.
Perfect. So whatever Lillian mentioned, find the slope at the time I turned it off. Right? Alternatively, I could have waited for the speed to get to 33% of the steady 33 or 37 or whatever that 1 by E term comes out to, right? And then figure out what the speed is, and then I could have done with the time constant, la la. Or another way is find out what the slope is right after I shut off the current. Right? So in this we looked in the forward differential, in this we'll do the backward differential. So our d omega by dt is going to be the speed right when it shut off. Right? One time instance before. So at t, from t equal to 0, we shut it off at some delta t, whatever the value was, and then subtracted from whatever the value is at the time we shut it off. This is what I'm going to call as 0 divided by our delta t value. And that is going to be a d omega by dt. What is this going to be equal to? Is it going to be equal to tau em by j? We got to be a little bit more careful here. What is it going to be equal to? So this term we are going to assume it to be 0. We are not applying any load torque. We have now shut off the electromagnetic torque, but before the time we shut off, there was an electromagnetic torque, which we know from measuring the current. So we have the reading for electromagnetic torque. So can I just do tau em by j and call it that as d omega by dt? That is what I did here, right? I did d divided by L and called it df by dt. Why was I able to do that? Because the current was very close to 0. In this case, is omega close to 0? Not at all. So whatever TEM, I need to subtract d omega and then divide it by d omega by dt, that will be r. So this is going to be whatever TEM is. TEM I can directly get from measuring the current, kT times I, before the time instance where I turned it off. So this is that time, negative delta t. Right? Figure out the electromagnetic torque, subtract d omega. Omega again I know from measurement. And this divided by j is going to be dw by dt. And then I can get j by just doing TEM minus d omega divided by d omega by dt. Right? So this is how you'd end up estimating all the 5 parameters. So here I estimated R, L, K, J, and B. How do I estimate KT? Do I need to estimate KT? No, right? Because K is already known, K and KT are the same. Okay. Any questions so far on how we estimate the motor back? No.
Why do we need to do it that way where it's like on and then we turn it off? Like why couldn't we just apply a current spike?
Oh, we can. So the problem with applying the current spike is the electrical system keeps changing with the mechanical system. Right? And the electrical system, in the previous case, we can assume that the mechanical system can't catch up with the electrical system. So the mechanical system didn't interfere with the electrical model. But the electrical system actually operates way faster than mechanical system. So we can't do the reverse assumption. So if our electrical system is changing, we cannot ignore those changes when we analyze the mechanical system. So we need to ensure that the current in the electrical system has gone to 0. Right? Before we can do this analysis. As soon as I turn off the voltage, the current wouldn't go zero like this, right? Because we have inductance there. But it goes to zero extremely fast compared to the mechanical system that I cannot more or less assume this to be a straight vertical drop. And then once this electrical system is out of the picture, then I can start analyzing the mechanical system as if it's the only system available. All right, but I can't do that analysis when the current is increasing on the turn on time, right? Because their current is gradually building up, all of these terms are varying. So this is definitely interacting with the system at that point, right? Okay, any other questions? Okay, so with that, let's look at a couple of examples on how to design controller in the frequency domain. So what we have is, we have our motor. The load torque of the motor is controlled by some other external thing that we have no say over. If it is a generator, it's the opposite, right? So let me draw what we can control. We can control the voltage of the motor and the load torque is whatever it is. If it is a generator, it's the opposite. We control the torque going into the generator and the voltage is whatever it comes out to be. Right? We will then have some kind of closed loop control to figure out whether the voltage is up, allowed, is the correct value that you want it to be, and then adjust it some prime mover mechanism to adjust the torque and so on. But let's consider just the motor case where we control the voltage, load torque is whatever it is, and the motor goes and settles to some speed, omega. Now we already saw a bunch of problems. As we start to increase the load torque, even for a given voltage, the omega starts to change. And then as the motor parameters changes, as the motor heats up, as the current increases, core saturates, and then we haven't even looked at what the B and the J terms changing, right? B term can change. Let's say you have some kind of liquid, a non-Newtonian fluid that you're mixing, or let's make it simple. Let's say you have a cement mixer. As the cement thickens, the friction of the fluid starts to increase. So we can have mechanical systems where B actively changes in the system as the system operates. Can somebody give me an example where a J will change, inertia, as the system keep operating? Yep.
If like the radius of whatever of the load changes.
All right, can you give me an example? A case where things don't break down.
If like a crane has to pick up a different amount of load
There would be change in the towel, load torque increasing.
in,
Something where, so let's say you have a machine that's rolling paper roll or something, or rolling huge cables. Right, you have seen those cables that they lay out on the side of the road when they have these underground wires going. You see the whole road. So when the machine kind of rolls those wires, as the radius of the roll increases, the inertia starts to increase. So your system inertia can change, B change, all of these systems can change. As these changes, we still want the speed to be a constant. So how do we ensure that? So what we do is we put some kind of control mechanism here. We don't know what that is yet. So we look at what speed we want it to get to. So this is our reference speed or the desired speed. And it needn't be a constant. We can make the motor rotate sinusoidally too. We can make the speed go like a sine wave. And when we do the lab, remind me, because we can try this out and we can get the different tones, right? The different tones of the piano. You can, by just changing the frequency, you can hear the audible tone changes, go from one frequency to the other. So we can take it to whatever speed we want and we measure what the actual speed is. So this is omega feedback, right? This is the actual. And based on the difference, we make some decision here to apply some voltage. Intuitively, we have a feel now that if I want to get to some speed and the actual speed is less than where I want to get to, what do I do to the voltage? Would I increase it or reduce it? If my current speed is lesser than the speed I want to go to, what would I do to the DC motor speed, DC motor voltage to get the speed higher? Increase it. So we need to increase it if the W feedback is less than W reference. And the opposite, if we are rotating at a faster speed than what we want to get to, we know intuitively now, not even intuitively, from math of it as well, that the speed has to go down in the opposite case. Sorry, the voltage has to go down if the speed has to go down. Right? So whatever the decision block here is basically going to do this function where depending on what the error is here, it's going to make some decision and decide what the voltage is going to be. Okay. So Let's look at a real world example. So let's say you have a car. That is your plant. In our case, the first case, the plant was our motor. And we measure some speed in the speedometer. And our brain takes some action while we are driving. We want to go to, let's say, 60 miles per hour on a 40 mile per hour road. And we look at what the actual speed is. And we got to make some decision here to figure out how much we press the gas pedal. So let's start out with a very simple system where I just have some kind of proportional gain. Let's say this gain is some number, doesn't matter. Let me call it Kp for proportional. Okay. Proportional P controller. So it's a proportional controller. So we feedback. This is coming from speedometer. This is coming from the speed limit. And then we make some decision. So very simple. If I want to go to 60 miles per hour and my speed is currently 40 miles per hour, then I know I need to increase the force I apply on the gas pedal, increase the gas so that the car can accelerate and go to the speed that I want it to go to. If I'm very close to 60 miles per hour, let's say it's 60 miles per hour speed limit and I'm already at 58 miles per hour, I don't want to press my gas pedal as hard as before, right? So the amount I press the gas pedal is proportional to the error that I'm observing there. If the error is large, I need to press the gas pedal very hard so that I can create more force on the engine, and then that can then accelerate the car. If the error is very less, I don't want to accelerate too much because I would end up overshooting. And the opposite as well applies. If I'm going at 60 miles per hour, the speed limit changes to 40. So my reference speed now changes to 40, but my feedback currently is 60. So I would start to take the leg off the pedal so that the speed starts to come down. If it was an electric car, when you take the pedal off, it starts to regenerate energy from the rotor so that you can take the speed down much, much faster. In case of a gas engine, there is nothing you can do to recover the energy back. It's just lost in the friction, or you can put a brake and then accelerate the rate at which it starts to fall down. Right? Will this system work in real life though? Right? Anybody says it won't work? Okay, Christopher, what is the problem?
Well, this is just like one source of error. You could have noise injected into your signal that screws up the gas pedal and creates oscillations. So
Okay, let's say this is a system where there is no noise. Will it
I'm
work?
saying just within the proportional gain.
Yeah, just with the proportional gain, will our system work? Ganesh, do you have an answer?
No.
No?
Yeah, I mean,
What will happen? Let's say I want to go at 60 miles per hour and I reach 60 miles per hour. Error goes to 0. Then this tells me that I don't need to apply any force on the gas pedal. From experience, all of you have driven, doesn't matter if it's car or bike or whatever. Can you remove the leg of the gas pedal and expect the speed to remain a constant? No, right? So there is something missing in the system. That once the error goes to 0, we know from experience that even after the error goes to 0, we still need to apply some force on the gas so that there is motion that goes on at the same speed. So some information is missing. When will I need to no longer apply, in what world, in what hypothetical world would I not need to apply any more force on the gas once the speed matches?
There's no friction on the car.
No friction, perfect. So when there is no friction in the system, when there is no loss in the system, then you can remove your leg and the system will go at whatever speed it was before. In a real world system, that is not the case. So I need to include something else in this model, some other control block that can ensure that even after the error goes to 0, even if the error is 0, the output is non-zero. Right? Because that's what our brain is doing. Our brain is doing nothing special. It is just basically looking at the error, and from experience, we have created a neural map which basically implementing this very simple function. Even after our error goes to 0, we know from experience that the pedal needs to be pressed. So what linear continuous system can I use to make sure that happens? Even if the input goes to 0, what operation in the linear continuous system would ensure that the output does not go to 0? Integration. So let me plot let's say this is my reference speed Vref, right? And this is the feedback VFBK. Now, if I plot the error between the two, it is going to go like this, right? Now, if I integrate this error, I'm going to have a value like this. Even after the error goes to 0, I'm going to have a non-zero output value, right? So if I put an integrator here, I can ensure that even after the error goes to 0, I can still generate some amount of output, which can keep pressing on the gas pedal and continue to keep driving the system. Right, so all we're doing is basically integrating the area under this curve. Right, it's just a weighted time interval sum as the time interval goes to 0. So if I replace this with an integral block, we can ensure. And let me add a gain as well. Why just integrate? If I can increase the scaling factor of this. Why just have this waveform? I can also have a waveform that's much larger, or even larger, or even smaller, or even smaller. I'm just going to give that element of control variability for me, and we'll later see why I'm introducing that variability. I could have directly taken the error and integrated, but sometimes it might make the system stable, sometimes it might make the system unstable, but I can choose a correct K value so that the system has a response just the way I want it to, right? So this is called an integral gain. Integral gain or an I controller, and the combined thing is called the PI controller. Right? Quite simple control. This is what we're going to be using throughout the rest of the course. And couple of interesting things. What happens if I increase the KP value in the real world? What would you call a driver who has a very large KP value in their head? What was it?
Lightfoot,
Could you repeat it?
a Lightfoot.
A Lightfoot, or basically a rash driver, right? They see a tiny difference in the speed and you just hit the gas pedal pretty loud. And as you age, hopefully this KP value starts to come down in your head, right? That's all that happens in your brain, nothing too complicated. So we want to intentionally create some values here and see what the responses are going to be. But before we do that, let's quickly go to the frequency domain, because how we design the KPK values will determine how our response is going to be. So if your KP gets too large, you know from experience that your response, let's say you're sitting with someone who drives extremely rash, versus you're sitting in the car with your grandpa. If the speed limit is 60 and you're starting off at 40, your friend response would probably look like this, while your grandpa's would probably look more measured. Right? So the difference is basically the KP that's causing the difference in the response. One is just a more measured experience, and the other one is just a lack of experience in some sense. Right? So we want to be able to, sometimes this is very useful if you're in a hurry. Sometimes this is very useful if you don't want to damage your car. In real world also the same thing happens. When you have a robotic arm application, right? You want to go from say some angle 30 degree to 120 degree. You don't want your assembly arm and your manufacturing plant to swing around, because there could be a person on the other side, there could be some equipment on the other side that could be damaged, right? So you want it to have a more slower response is okay if it doesn't overshoot. But another application like an EV application, say Tesla boasts that they can go from 0 to 60 in less than a couple of seconds, that boasting factor has a lot of value. They don't want this kind of response, right? If you set a limit of 60 and your car goes to 62 miles per hour, nobody is going to penalize you for it, right? But if it takes a long time to get to the 60, people are going to penalize you for it. So they would have this kind of response in their auto driving system, where they would exceed a little bit, but the settling, it would make the user feel as if it got to the settling point much sooner than the other response. So we want to have different kind of controls for KPK value so that we can get any kind of these response that we need to based on the applications that we have. So to do that, we will be looking at the frequency domain. So, which we will do on Friday. So for today, let's just do a quick refresher. Let's say I have a transfer function G of S. how do you figure out if the transfer function is stable or unstable?
If the poles are on the left half plane.
Right, so the poles are on the left half of the plane. So let's say this has some numerator, some denominator. So whatever the solution of this characteristic equation is. Okay, so some denominator of S, set that to 0, solve for the equation. Let's say it comes out to some S plus alpha, S plus beta, S plus gamma equal to 0. And then of course the poles are S equal to minus alpha, minus beta, minus gamma. And if these alpha, beta, gamma terms are positive, or in the other words, the poles are negative. So the solutions of the characteristic equation of the denominator is called the poles. If you do the same solution for the numerator of S equal to 0, the solutions, whatever comes out would be called the zeros. Right? So if the poles, if this negative alpha term, negative beta term, negative gamma term are all negative, that is alpha, beta, gamma are positive themselves, then the solutions are stable. Then our system is called stable, otherwise the system is unstable. Why should they be negative? Why is it stable only if they're negative? What happens in the time domain?
Don't the complex exponentials like go to 0?
Okay, so once I have this representation, I can then decompose it into some S plus alpha, some B by S plus beta. I can just split the fractions. Right, and then once I take the Laplace inverse of this is just going to be some A times e power minus alpha t plus B times e power minus beta t plus C times e power minus gamma t. So I better have this negative gamma, negative beta, negative alpha terms be negative. Otherwise, as time goes to infinity, this term would become larger and larger. Right? One of the requirements for stability, or actually the only requirement for stability, is that if you have a bounded input, the output must be bounded. If I give 10 volts and the motor speed goes on increasing and increasing and increasing, then the system is unstable. If the motor speed starts to come down, then the system is stable. Is a DC motor a stable system or an unstable system? I haven't designed any control loop, just the system alone. Is the system by itself stable or unstable?
Stable.
Stable. There are multiple ways we can answer that, right? Because well, the easiest way is look at the transfer function. The poles are R divided by L, right? Sorry, the poles are negative R divided by L. So we have S plus alpha, the poles are S equal to minus alpha. So negative R by L, so that's a perfectly fine value. So our system is going to be stable. Another way of looking at this would be this is a real world system where if we put the energy is V times I on the input, the energy at the output is tau times omega. If we put some finite voltage, then it's going to have some finite amount of power going in. If the speed keeps on increasing, then it will have infinite amount of power at the end of the day. Right? So we can't create energy out of nowhere. Can you give me an example of an unstable system?
Inverted pendulum.
Inverted pendulum, perfect. So when you have an inverted pendulum, or as kids you have played with ladles, inverted, or you would have these wires and try to walk across them or bike across them, those are all unstable systems. Right? You have poles which are on the right hand side of the plane. So in our case for the motors, we have a stable system, open loop stable. Then why are we designing a control system? The system is always stable to begin with. What are we trying to stabilize? When we have this inverted pendulum example, we are trying to actually stabilize the inverted pendulum. Left to its own, it would fall down. Right? If you don't do the proper control, the system is quite unstable. So there, the purpose of the control system was to stabilize it. What is the purpose of our control system? The system is already stable to begin with. What are we designing the control system for? Yep, Christopher.
Aren't you like trying to target a specific torque or speed?
So our purpose is not to stabilize the system. Our purpose is to get to a particular speed that we wanted to get to, right? So our intent is different compared to where we actually want to stabilize the system. Okay. So we have a system is stable if so the idea is the system is going to be stable if the poles are on the right hand side of the S plane. The zeros themselves do not matter for stability. They would cause what's called a phase delay, but otherwise it won't affect too much. In our case, we won't experience a zero in the control system that we have, so we're not going to worry about it. Right, so let's look at a couple of examples. If I have an open loop system that's unstable, can I stabilize it using closed loop? Right, so that's what the inverted pendulum case is. You can stabilize it. When you balance an inverted pendulum in hand, your I is basically the closed loop that's doing the stabilization. So let's say we have a system, some 4 divided by s minus 1, g of s. This is clearly unstable because the poles are on the right side. Our time expression is going to be e power 1t. Then this is going to exponentially blow up with time. So the way we can stabilize it is put this with a simple closed loop, g of s, and close the loop. I can use a transfer function, some kind of control system on the feedback as well, which we typically don't. It will typically be some gain blocks, but in this case, we don't even need that. What will be the closed loop transfer function for this? What is the closed loop transfer function? What would be the closed loop transfer function? That's basically output divided by input. Right? What would that be for the system? Very simple transfer function. So it's g of s divided by 1 plus g of s, h of s. In our case, h of s is just 1. So once you substitute this, you have 4 divided by s minus 1, 1 plus 4 divided by s minus 1. So we have 4 divided by s plus 3. And thus we have stabilized an unstable system, right? Just by putting a simple closed loop control. Okay. So going back to this, if I just look at this term, 1 plus g of s h of s, can this system have poles on the right hand side and still be stable?
They're canceled out.
If they are cancelled out, otherwise they will be unstable. So going back to this 1 plus g of s h of s, what was that here? So we had s plus 3 divided by s minus 1. So I should have rephrased it. If 1 plus g of s h of s has poles on the right hand side, will the closed loop system be stable or unstable? Can we tell anything about the stability of the closed loop system based on the poles of the denominator? 1 plus g of s h of s transfer function. Absolutely not. Because here, from looking at 1 plus g of s h of s, 1 plus g of s h of s is unstable. But in the closed loop system, it did create a stable system at the end of the day. 4 divided by s plus 3. Right? Which part of this 1 plus g of s h of s do we need to look at to figure out whether the closed loop system will be stable or unstable? Clearly, the denominator is useless. Right? In the denominator, we had s minus 2, s minus 1. But in the closed loop system, the denominator plays no role because the numerator's denominator and the denominator get cancelled out, playing no role at all. So you could have s minus 1 here, s minus 2, s minus 3, s plus 1, it really doesn't matter. Which part of 1 plus g of s h of s matters when we look at the stability of the closed loop system? The numerator, perfect. So Fiona, right?
Yeah.
Yes. So the answer Fiona gave is look at the numerator, that's what matters. Because if you look at this s plus 3, that is what comes out as the final denominator in your closed loop transfer function, right? So if you want to look at the stability, so when you have a transfer function, when you have a simple first order transfer function, you can go through the trouble of finding out what the closed loop transfer function is and looking at what the poles are and so on and so forth. But you don't even need to go through the trouble. All it says is just look at what 1 plus g of s h of s and look at the numerator alone and you can infer the stability of the system. All right? Everybody clear so far? Okay. So we don't need to go through all of this math, and it's particularly useful when you have higher order systems where you don't have to solve the roots for it. Up to what order can we actually get an analytical expression for the roots of a system? Can we remember the theorem from your numerical analysis course or something? So if your polynomial, the characteristic equation is up to 5th order, you can get an analytical solution. After fifth order, there is no analytical solution. So if you have S power 6 plus S power 5 plus S power 4, blah, 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 something, you can't get a nice analytical expression. Like for a quadratic, you could get minus B plus or minus square root of B square minus 4AC divided by 2A. That is not, you can't get those formulas for order greater than 5. Right? You can do numerically and get individual solutions, but you can't get a general expression. So higher order system becomes quite complicated. So we want to simplify the system as much as possible. Okay, so the idea is, if you look at the numerator of 1 plus G of S H of S, we are good to go. So let's look at just 5 examples. Again, those of you have to leave this, okay. Just want to introduce this so that we can continue next class. So let's say my transfer function is S plus 1, F of S, some complex system. And what I want to do is I want to look at, so the zero of this, if I plot this in the S plane, the zero of this is going to be at S equal to minus 1. Right? Now what I'm going to do is I'm going to look at 4 different spots surrounding the zero. And I want to figure out what F of S looks like. So the values are S equal to 0, S equal to minus 1, the J, right? So this is the J axis, this is the real axis. So minus 1 is here, J is here, this is minus J, and then this is minus 2, J0, and then this is again minus 1, minus J. So I want to start from this, go to these 4 points, and look at what F of S comes out to be. So let's say this is S is 0, minus 1 plus J, minus 2, minus 1, minus J. For the first one, what is F of S? Straightforward, right? Just substitute S equal to 0 there, you get your F of S, that is just 1. So take these values, substitute into this function S plus 1. The second one, the value comes out to J. The third one, the value comes out to negative 1. Fourth one, the value comes out to negative J. So on the right, I have plotted S values of the S plot in the S domain. Now I'm going to plot the values for function F of S. Right? So this is again the real axis. This is the imaginary axis. So this is the plot of values of S. That is the plot of values of F of S. And remember, the direction in which I went is anti-clockwise. So I started from this point, went to this point, went to this point, went to this point, and came back to this point. So I'm encircling this 0 in the anti-clockwise direction, right? And I want to see what curve comes out on this side. So for 0, I got F of S as 1. For 0, I got F of S as 1. So the solution for the first value, right? The answer was 1. Then we went to J for the second. So the second result was J. The third result was negative 1. This is the third one. And then the fourth value was minus J. So if I go back and complete this, so I just took 4 points to keep it simple, but I can flush this out with like 100 different points. I would get a more continuous distribution. And then come here, come here, come here. So what can I tell about the F of S curve? If my S-plane curve encircles a 0, by 0 I mean the roots of the solution of the characteristic equation, right? Which is S equal to minus 1. So my curve, my contour is encircling the 0 in the anti-clockwise direction. What can I tell about the F of S plot? It is going to encircle the origin in the anti-clockwise direction as well, right? So if I have some transfer function which has poles, and if I took a curve that encloses, zeros, and if I took a curve that encloses that 1, 0, then in the F of S domain, I would get the same anti-clockwise direction, but encircling the origin, right? When I look at the F of S plot. Now, on Friday, we'll do the rest of the 4 examples, but just to think about it, if instead I had a 0 here, pole here, how do I change this transfer function to create a pole here instead of a 0?
Negative 1.
Not a negative 1. If I put a negative 1, that will push the 0 to this side. What is the difference between a pole and a 0?
1 over.
1 over Perfect, answer Jack. Okay, so the zeros are the solutions of the characteristic equation of the denominator. Poles are the solution to the characteristic of the denominator. So if I introduce a pole here instead, and if I do the same encircling in the anti-clockwise direction, what we will observe next class is that we would encircle the origin in the f of x plane in the opposite direction. Alright, so zeros, if you encircle in anti-clockwise, f of s will encircle origin in the anti-clockwise. Poles, if you encircle anti-clockwise, same anti-clockwise in the s plane. In the f of s plane, the direction will reverse and will become clockwise. Right? So we will look at more examples next class and then look at Nyquist stability criterion. With that, we are done. Thank you. And please don't forget to fill out the time slot